Control of the generator output voltage is affected by adjusting the magnitude of excitation current. We already know that increasing excitation results in an increase in the strength of the rotating magnetic field. This in turn brings about an increase in the voltage, which is induced into the stator conductors. Let's take a closer look at the excitation system to see how this control is carried out. First, we'll look at a simplified arrangement of the static excitation system. DC current from the rectifier is supplied to the rotor winding through the collector rings on the shaft. The incoming AC to the rectifier is supplied from a dedicated transformer. The primary side of this transformer is fed from an auxiliary bus, or in some cases the generator bus itself. The sine wave for the incoming three-phase AC voltage, which is applied to the rectifier, will look like this. After rectification, the DC output can be represented by this curve, and this may be further smoothed to look like this. The level of DC voltage can be adjusted by controlling the firing of the thyristor type rectifier. The firing circuit itself is controlled by the field voltage regulator. This regulator has two inputs, manual and auto. The manual control disconnects the automatic function and allows the operator to directly control excitation. However, when the generator is in operation, the field voltage regulator is usually controlled from the auto position, that is, from the AC voltage controller. This controller monitors the generator bus output voltage through VTs and automatically adjusts excitation so as to maintain the set point voltage. The operator can adjust this set point and thus exercise control while the excitation system is operating in auto. All of these components of the static excitation system are normally located in a so-called excitation panel close to the generator. Of course, the auto and manual control inputs will also be located on the operator's panel. Another type of excitation system often used with gas turbines is known as the brushless exciter. The exciter is actually a small AC generator which is built onto the end of the generator shaft instead of collector rings. In this exciter, a stationary magnetic field is provided from the DC winding, which is wound on the stator. The rotor winding produces AC voltage, and this is fed directly into diode-type rectifiers, which are built into the shaft. So we have, in effect, a rotating rectifier. The DC output from the rectifier is connected directly to the main rotor winding through leads which pass inside the shaft. There is no need for collector rings or brushes. An exception is shown in your workbook where the generator is used as a startup motor. Control of the DC excitation current is affected by adjusting the strength of the exciter magnetic field. And this is done by controlling the DC current flow through the field winding. This DC field current is supplied from a rectifier which is located in a nearby cabinet. Of course, this rectifier is much smaller than the static rectifier that we previously studied because it is supplying field current only to the rotating exciter. But control is effected in the same manner. That is, by adjusting the firing of the thyristors. And this in turn is governed by the field voltage regulator. The arrangement at this point is similar to the static exciter. When in auto, the field voltage regulator receives its command signal from the AC voltage controller, which in turn monitors the output voltage of the generator. The operator can adjust the AC set point as required. When starting up the unit, the field voltage regulator may be set to manual, and in this case the operator will control the regulator directly. So what is the effect of adjusting excitation? Well, obviously one effect is to adjust the output voltage of the generator. For example, by increasing the excitation current, the generator terminal voltage will increase. But that's not all that happens. As terminal voltage is increased, the generator will produce and transfer more megavars into the power system. On most units, the megavar output of the generator is indicated right alongside the megawatt output. The term megavars stands for megavolt amperes reactive. It is actually the unit for reactive power. But what is this reactive power? Well, it is a fact of life that all electromechanical devices, such as transformers, motors, electromagnets, etc., all of these require megavars in order to set up and maintain their magnetic field. For example, let's look at an electric motor. The shaft on the motor rotates to drive a machine and produce useful work, let's say 100 horsepower. The motor will need to draw about 75 kilowatts in order to produce this power output. But in addition to this, the motor will need to draw about 30 kilovars in order to set up the magnetic field which is needed for the motor to function. So on our power system, we have a demand not only for megawatts, but also for megavars. And both of these power components must be supplied by the generators. Fortunately, the provision of megavars does not require any increase in energy input to the turbines. The fact is, reactive power does not absorb any energy at all. The reactive power actually oscillates twice per cycle between the magnetic field of the generators and that of the consumer's equipment. The average power consumed is zero. So why are we concerned about this reactive power? Well, the problem is that even though increased energy input is not required, increased current still flows through the generator windings and through the power system. The result of this is that we could easily overheat the generator windings if we had a high megawatt output plus a high megavar output. Distinct limitations are placed upon the combined total output of megawatts and megavars. Megawatts and megavars act with a different phase relationship to voltage. Active power is in phase, while reactive power acts 90 degrees out of phase. The combination of megawatts and megavars is known as MVA, that is megavolt amperes. You will remember that in a DC circuit, if we multiply volts times amps, we get power, watts. However, in an AC circuit, volts times amps, VA, gives us apparent power, as it is a combination of vars and watts. The ratio of true power, that is active power, megawatts, to apparent power, megavolt amps, is known as power factor. This curve shows us the limitation of MVA due to current in the stator. For example, at this megavar loading, we can only produce this amount of megawatts to stay within the machine's capability. Clearly, in order to keep within the MVA rating, we must reduce megawatt output if we wish to produce a large output of vars on the generator. However, there are other limits to observe in generator operation. As we know, in order to increase the megavar output of the generator, we must increase excitation. The increase in current flow increases the heating of the rotor winding. This curve shows the limitation due to rotor heating. You can see that we can operate this generator at 180 megawatts and 0 megavars, but if we needed to produce, say, 100 megavars, then we would have to reduce the megawatt output to 140 megawatts in order to keep within the established limits. We also run into trouble if we reduce excitation too much. In this case, as the voltage falls, vars will flow into the generator from the power system. This is shown on this curve as negative vars. The problem is, if the rotor current is reduced too much, then the magnetic field may become so weak that the generator will lose stability and fall out of synchronism with the other units on the system. In order to prevent this, a minimum excitation limit is established by this additional curve here. This combination of limits provides the generator capability curve that you should be familiar with. For each specific generator, this curve is normally displayed in the control room. Make sure that you always operate the generator within these limits, whether you are absorbing or supplying megavars and megawatts. Okay, now that we've got you interested in this subject, I have to point out that any further discussion is really outside the scope of this program on gas turbines. If you would really like to know more about electrical system operation, please refer to other of our video programs. Most power companies already have our video programs on power system operation and power system protection and others. At this time, please switch off the videotape and thoroughly review this material in your workbook.